on October 19th, 2017, the report came out and they said, well, it's an interstellar object, but actually the first email reporting about it already said, it looks really strange because the amount of light reflected from it was changing every 8 hours as it was tumbling. And it was changing by a factor of 10, which is huge. I mean, the biggest variation for solar system objects before was about a factor of 3, okay? Now, what does it mean? It means that the surface area of the object projected on the sky because changes by of order 10 because that surface reflects sunlight. So just imagine a piece of paper tumbling in the wind. Even if the piece of paper is razor thin, extremely thin, it's unlikely to be aligned edge on to your line of sight. Okay, so a variation in the area of the piece of paper as it's tumbling by a factor of 10 means that it really has an extreme geometry. Because if you were to take a football shaped object or a cigar shaped object, they would, unless you make the cigar 10 times longer than it is wide, it won't show these variations in cross-sectional area. Okay, so that already made the observers quite intrigued. And this data was so intriguing to me that I wrote an email to Yuri Milner, an entrepreneur in Silicon Valley that I was in contact with, and I was supposed to visit his home a week later, and he funded the Breakthrough Listen project, which is aimed at listening to radio signals, perhaps from extraterrestrial civilizations. That's a search, and as I mentioned before, it was done for 7 years, but he put much more funding behind it. So I met him at his home, and I said, look, this object is intriguing. I already mentioned that in my email that it could be of technological origin. So why don't we just check if there's any radio transmission from it? And he agreed, and then we checked, and it was less than a cell phone. So it was 0, basically. So we didn't detect any radio signal. But to me, it was intriguing that its shape is so strange. And then more and more facts about it were recognized. First, that it came from a very special frame of reference, the so-called local standard of rest, which is sort of like the rest frame of the galaxy nearby. Like the stars are moving relative to each other with random speeds, but when you average those, you end up in the local standard of rest. And the sun is moving relative to that frame at tens of kilometers per second, but this object was nearly at rest, which is very unusual because if it came from a star, only 1 in 500 stars is so much at rest in that frame. So that was another strange thing. Then it was realized that it's actually being pushed away from the sun by some mysterious force that is not gravitational, and usually such a force is coming from the evaporation of comets when through the rocket effect, when material outgassing, when material is expelled in one direction, in preferred direction, the object is pushed in the opposite direction, just like a rocket. But there was no evaporation visible, and actually the Spitzer Space Telescope looked very deeply and couldn't see any traces of carbon-based molecules or dust around it, so it was definitely not a comet. So what is pushing it? And to me, all of these were quite intriguing, and at some point, once this non-gravitational acceleration was reported in Nature magazine, I decided, well, maybe I should write the scientific paper suggesting that it's artificial. And I wrote several articles to Scientific American in the months preceding that, suggesting that it may be technological in origin. So then, together with a new postdoc, Shmuel Bialy, that came to my group, we wrote a paper suggesting maybe it's very thin. It's just like a sail, a very thin object pushed by reflecting sunlight and not evaporating at all. Just by, the fact of being thin, it has a large surface area for its mass, so it's getting pushed. And we know of such things because we are designing light sails, basically sails pushed by reflecting light, just the same way that the sail on a boat is pushing the boat on a sailboat by reflecting the molecules of air in the wind that is pushing it. And so in the same way, you can reflect light and get pushed if the object is thin enough. And we calculated it needs to be very thin, but I wrote a paper a few months ago suggesting maybe it was a piece of what is called a megastructure, like a Dyson sphere. Freeman Dyson, about 60 years ago, imagined that an advanced civilization will construct a big structure around its star to harvest the energy output from the star. When we are talking about clean energy, it's the energy impacting the Earth. That's a very small fraction of the total area surrounding the sun, and it's about 1 part in 100 million. So imagine a civilization that wants to harvest 100 million times more energy than we can get on Earth from the sun. The way to do it is to surround the star with a megastructure. And if you look at the engineering aspects of it, the best way to do that is to have tiles, each of which is floating over the star by the radiation coming from the sun or the star, pushing it out at exactly the same force as gravity is pulling it in. So it's basically hovering, just like a kite drifting in the wind. That it can drift above the star, and you put a lot of these tiles, you build what is called a Dyson sphere, so that you harvest the energy. And then imagine the star evolving, just like we talked about before, getting brighter. Then these tiles will break apart, okay, because the radiation pressure now will exceed gravity. And so they would become interstellar objects. Very easy to lift them out of the gravitational potential well, because they're already very marginally bound. So maybe Oumuamua was a piece of that, a tile of that kind of megastructure. So at any event, we don't know what it was, but the suggestion was maybe it's very thin. And I should say the paper was accepted for publication within 3 days. That's a really very fast turnaround, unprecedented. Moreover, the referee said, in fact, there is evidence that the object is flat. So that supports your idea. And indeed, about a year later, there was a paper that appeared in the Astrophysical Journal, in an Astrophysical Journal, monthly notices of the Royal Astronomical Society. And in it, there was a detailed analysis of the variation of light reflected by Oumuamua. And the conclusion was that at a 90% confidence level, this object had the geometry of a flat surface, not cigar-shaped, the way it was portrayed in some artist illustrations. Obviously, if you look at a piece of paper that is tilted in your direction, it looks like a cigar projected on the sky, but it was most likely flat. So the referee actually supported us. And then once the paper was, immediately after that, there was a huge media storm. I was about to go on a trip to Germany, and just a few days later, and there was a TV crew at the front door just before I left to the airport in Boston, and I said, I'm sorry, I have to go. And they said, well, we just have one question. Are we alone? And I said, I don't know, but this object looks weird, and I left, and there was no Wi-Fi on the flight. But when I arrived there, I had Good Morning America. I had my email inbox was full of requests. Then when I arrived to dinner there, it was a very prestigious forum. It's called the Falling Walls in Berlin, and lots of distinguished speakers were there. And I went to dinner. I didn't know any of them personally, but they said, oh, we know who you are because you just had this paper that appeared everywhere. And then the following day, there were 25 reporters put in one room because all of them wanted to speak with me at the same time. And it was sort of like a press conference, but I didn't expect that. And then they, there was an Italian reporter from the back of the room. She shouted, so do you think you are Galileo? And I said, I'm not trying to be Galileo. I'm just talking about an object that looked weird, obviously it will change our perspective about our place in the universe. Galileo did realize that we are not at the center of the world. And he realized it by seeing the moons move around Jupiter, so they are not moving around us. That was a very simple argument. Here is something in the sky that is not moving around us. Obviously, it's possible the Earth moves around the sun. Okay? And of course, the clergy didn't want to look for his telescope at the time. But I'm not making analogies. I don't, it's not, science is not about analogies. It's about evidence. And here the evidence points in an anomalous direction. So that's intriguing. Let's find more evidence. And a couple of years later, we discovered 2 interstellar meteors. The first, actually one of them was from 2014. It was the US government data that was cataloged by NASA. And, I was asked for a radio interview about the meteor that landed near over the Bering Sea near Kamchatka, 2019, January 2019. I was interviewed about it. Just a month earlier, it was documented. And I didn't know anything about meteors, so I started Googling it. And because I worked, as you said before, I worked on black holes, I worked on the first stars, but not on meteors. And so I then realized NASA has a website where they put a catalog based on US government data, which was collected, as a result of the US government wanting to find out whether there are ballistic missiles fired at the US, so they're monitoring the atmosphere of the Earth, and every now and then they see a fireball. Has nothing to do with national security, and they say, okay, well, that's an object that collided with Earth, okay, and it came from a distant source, so we just put it out in the public domain. So these are the meteors, 273 of them. So I realized, that's wonderful, because they give the velocity components of each meteor. And so I asked my student, Amir Siraj, I said, look, there was this interstellar object, Oumuamua. Let's check this meteor sample and see if any of the meteors is moving too fast to be bound to the sun. If we go back in time, okay, it's very easy calculation. And we checked, and he came back to me and said, yes, there is one that is clearly of interstellar origin, this one. And we then wrote a paper about it. But by that time, the community of astronomy was up in arms against any conversation mentioning the possibility of technological origin of anything. So we submitted this paper, and the experts on meteors said, we don't believe the US government. So I thought to myself, well, that's an interesting standpoint, because, the point is the catalog didn't have any error bars because the US government doesn't want to disclose the quality of the sensors they're using for national security purposes. And I said, well, they must know whether a ballistic missile will hit Boston or New York City. They must have very good precision. But no, the paper was rejected from publication. Okay, so then I was at the time the chair of the board on physics and astronomy of the National Academies, and at dinner I mentioned this situation. I gave a presentation and I mentioned to the board members, I said, look, this is an intriguing meteor. We are pretty confident it's actually moving at 60 kilometers per second relative to the sun outside the solar system. It's a very confident, with great confidence, we can say that it's interstellar. It's not just marginally unbound to the sun. It's moving faster than 95% of all the stars in the vicinity of the sun, based on the data. And so one of the members of the board was from Los Alamos, and he came to me and said, I will try to help you to declassify the error bars, the uncertainties in the measurement. And it then took 3 years until someone from the White House named Matt Daniels was enabled, basically, a letter from the U.S. Space Command under the Department of Defense to NASA, stating explicitly in March 2022, that was 3 years after our paper came out, stating that our paper is correct and that they can state that this object, this meteor, was interstellar at the 99.999% confidence. Just think about it, 99.999% confidence. Okay, so they released it to NASA. It was publicly available. As a result, we resubmitted our paper 3 years later. And still, some people were unhappy, saying, well, that's just the government saying something. How do we know that it's correct? Well, if you look at astronomy, on many occasions, people report results. And you don't say, how do I know it's correct? If it's a transient event that happened only once. And why would you doubt, in this case, the Department of Defense came to my defense. That's really unusual. Why would the Department of Defense be so much in favor of blue sky research when the scientific community, like experts on meteors, would try to push back and reject it as much as they can? That is a very unusual circumstance. You'd expect it to be the other way around. And anyway, the paper was eventually accepted for publication, and the government also released a bonus. They gave us the data about the fireball of this meteor. And we were able to conclude that the meteor exploded at very high stress when it reached the lower atmosphere of the Earth, and therefore had a material strength that is tougher than all other meteors in the catalog, 272 of them. So why would the first interstellar meteor be of material composition that is tougher, stronger than all other space rocks from the solar system? And, people can argue, oh, maybe it's made of iron as well, like iron meteorites. That's not my point. My point is the catalog includes 5% of the meteors are iron meteorites. I'm not saying what it is made of. I'm just saying it's tougher than all the meteorites we had seen before in the catalog. That is a statement that cannot be disputed given the speed of the object and where the meteor exploded in the lower atmosphere of the Earth. It's tougher. And that's the first object from outside the sun. By the way, it predated the Oumuamua by 4 years. So now you have the first interstellar meteor being of material composition that is unprecedented based on space rocks. And we found another interstellar meteor. It was also tougher than all the others. So 2 interstellar meteors, the second one from March 2017, about 7 months before Oumuamua. And then you have Oumuamua being a weird shape, being pushed away from the sun by a non-gravitational force without showing cometary tail. And then the fourth object was a comet. Okay, so 3 out of 4 interstellar objects appear anomalous. And I say, that's intriguing. Let's collect more evidence. And my colleagues say, no. First of all, Oumuamua is natural. And, we don't really care what the natural origin is, but it's natural. So why do I say that? Because the first paper to say that said it's natural, period. It was a review paper in Nature. And then a few months later, there was a paper saying, well, okay, but it's indeed natural, but to explain the anomalous acceleration, we are suggesting that it was made of hydrogen, because then hydrogen would be transparent when it evaporates, and it would be a comet, but a comet made of hydrogen, which is not produced in planetary systems, produced in molecular clouds. We've never seen a chunk of frozen hydrogen, but beyond that, I wrote a paper a few months later showing that it cannot work because the hydrogen would evaporate very quickly and would survive the journey. And the authors of that paper said, yes, we agree. That doesn't work. Okay, so then that doesn't work. So what was the alternative? Then another group came out and said, oh, maybe it's a dust bunny. Cloud of dust particles, 100 times less dense than air on average, very fluffy. So when it reflects sunlight, it's getting pushed. So just imagine it being lighter than a feather, basically being pushed by sunlight. We've never seen such a dust bunny in space, the size of a football field. And the main issue is that when it gets close to the sun, it gets heated by hundreds of degrees, and it wouldn't survive. It wouldn't maintain its integrity because it's so fluffy. Just think about something that is 100 times less dense than steam, the coming off a pot of boiling water. Anyway, then another group said, okay, well, it's not a hydrogen iceberg. It's not a dust bunny. It's actually, we know what it is. We nailed it. That's the answer. And everyone said, yeah, that's it. And they said, it's a nitrogen iceberg that was chipped off the surface of a planet like Pluto. We have never seen a nitrogen iceberg, even though Pluto exists in the solar system. So they said, no problem. No. These are short-lived at the beginning of the solar system. There aren't none left in the solar system. But from other planetary systems, just imagine crashing all the solid nitrogen on the surface of Pluto's in other planetary systems and launching those chunks into space. And one of them, the size of a football field, is a nitrogen iceberg that came from the surface of a Pluto-like planet around another star. And everyone said, yeah, that's it. And nitrogen will be invisible. And it makes a lot of sense. So we checked out the numbers, the mass budget. You just don't have, if you make very optimistic assumptions, basically saying all the solid nitrogen on all the Pluto-like planets that you can imagine, is being broken into pieces, and you send all of those pieces to interstellar space, there is just not enough nitrogen in the Milky Way galaxy to account for a large enough population of chunks that would explain Oumuamua. Okay? So then, the latest is a paper that appeared in Nature just a couple of months ago, saying, in the abstract, it says, indeed, hydrogen iceberg doesn't work. Indeed, a nitrogen iceberg doesn't work. That paper says that. So we found it. Now we know what it is. We found it. And I should say this paper was not only celebrated by a News and Views article in Nature, but also by all major newspapers who said, now problem is solved. We know. And the solution is, it's natural, of course. Otherwise, why would they celebrate it? It's natural, and it is, now we know what it is. It's actually just a standard water iceberg that we see in the outer parts of the solar system, but it went through a transformation. When it traveled through interstellar space, cosmic rays, very energetic particles that penetrated it, converted about a third of the water molecules into oxygen and hydrogen. They broke these water molecules, and then the hydrogen, migrated to the surface of this iceberg. And again, we see the hydrogen. Well, that's the hydrogen that pushes the object. We don't see it because it's transparent. So it's a variant on the hydrogen model, except now you start with a water iceberg and you convert a third of the water molecules into pure hydrogen and oxygen. And they calculated the surface temperature of such an object at the distance of the Earth from the Sun and said, well, that's just the right temperature to release enough of the hydrogen and give it the propulsion that you need. The problem is they missed a term that is 1,000,000 times more important in the energy balance on the surface of this iceberg. Basically, they balanced the heat delivered from sunlight to the surface against the radiation from the surface. But they forgot to include the cost in energy required to dislodge the hydrogen molecules from the surface. So you need to invest some energy in kicking the hydrogen atoms out of the surface. And it turns out to be an extremely energy-consuming process that basically cools the surface temperature well below by a factor of almost 10 relative to the calculation that they had in the Nature paper. So we wrote a paper a day later after this Nature paper appeared and showed that they made a mistake in the energy budget. And I mentioned it to all the reporters that reported a day earlier about this Nature paper. And some of them said, we don't want to confuse our readers, so we will not talk about this issue. And my point is that, science should be delivered the way it's happening. So if there is an argument against this model, you may just put a footnote saying there is this other paper that says that something was missed. But no, it's better to maintain the narrative without, reporting about challenges that this model. So my point is, altogether, there were suggestions by the mainstream that this object is natural in origin, or Oumuamua is natural. All of them involved a rock or an object of a type that we've never seen before, and all of them have challenges. And given that, in my opinion, we should leave the possibility that it's artificial in origin on the table and just try to find another object of the same class. And I'm actually planning to do that with my students and postdocs, because there would be a new telescope. The way I think of it is dating the next Oumuamua. So we have a dating app, which is a telescope in Chile that called the Vera Rubin Observatory, that will have a survey of the sky, the southern sky, every 4 days with a 3.2 billion pixel camera. And it's very likely to find more objects like Oumuamua. And then we plan to extract those objects from the data stream of the Vera Rubin Observatory, and then follow up observing them, for example, with the Webb telescope, the James Webb Space Telescope, that will look at these objects from a different direction than Earth-based telescopes. And as a result, it's just like having two eyes. We can pinpoint the trajectory of the object to a great precision in 3 dimensions, because the reason we have 2 eyes is so that we can gauge the distance to a threat that was beneficial for us to survive in the jungle. And but in the case of the Webb Space Telescope and an Earth-based telescope, when looking at an object from 2 directions, we can gauge the distance very precisely and pinpoint it in 3 dimensions, and by that infer whether there is any artificial propulsion acting on it. And so that we can do much better than we could do with Oumuamua. And moreover, the Webb telescope can see the infrared, the heat emitted from it, and from that infer the surface area of the object, because we know the temperature of the object from its distance from the sun. And then as a result, we can infer how big it is and how much reflectivity it has with respect to sunlight. So these are things we couldn't pin down for Oumuamua. So there is a lot to be learned. We might learn about the material composition of the surface. That's why we need to find the next Oumuamua. And if, there are some astronomers that are obsessed with Oumuamua, they are thinking about chasing it. And I say that's the wrong approach, because, like if you came to a coffee shop and you saw some potential partners there, but by the time you realize it, they left through the door and they are now in the street and they didn't leave their phone number with you. It's a bad strategy to run after them, especially if they move very fast. I mean, they move, in the case of Oumuamua, it moves faster than our rocket. So it's really difficult to chase it. But instead of being obsessed with such a thing, you just look for other, Oumuamua-like objects or other partners that reflect what you liked about those that you saw before. So in this case, finding more Oumuamuas make a lot of sense. And in the context of the interstellar meteor, this summer, 2023, we will go on an expedition to collect the fragments left over from the first interstellar meteor. And then from the composition, we can tell whether it was artificial in origin or just an unusual natural object, this meteor. And once we collect a sample of whatever was left from it, already arrange for a place for it at the Harvard College Observatory. We'll analyze it with the best instruments. If we find a gadget, I promised the curator of the Museum of Modern Art in New York City that we'll bring it for display there, because it will represent modernity for us. And I asked my students in the last class of the semester, just a couple of weeks ago, I asked them, if you were to have, to encounter a gadget and it would have some buttons on it, would you press a button on an extraterrestrial gadget? And half of the class said, yes, definitely. They were curious to know what will happen if you press a button. Just imagine iPhone 100 or GPT 100 or whatever. And And half of the class was really reluctant. They said they will never press a button. And I asked, is it because you worry about yourself or humanity? And they said both. So then one student asked me, he said, what will you do, Professor Loeb? And I said, well, I would, as a scientist, I would prefer to first take it to a laboratory and examine, what it's like. And before engaging with it, it's sort of like capturing a traumatized, intelligent animal, like you don't engage with it until you figure out what's going on, and you just bring it to the lab and carefully engage with it. And that's what I would do as a scientist.
Well, a number of things. So one, I would also find it very difficult to resist pressing this button. Then two, right, with regard to chasing Oumuamua, not only can we not propel ourselves fast enough to catch it, but it's also so many millions of miles away that we lack the equipment to resolve it, so we can't continue to observe it, which is why this 11-day window in October of 2017 was so important. Then I think it's very, very cute to call this gaseous interstellar creature a dust bunny. And then lastly, to, I guess, continue our conversation, I want to come back to these two meteors and your journey to collect the fragments of one of them. But first, I'd like to get a bit deeper into Oumuamua, and particularly because of the psychology of your critics and colleagues in the astrophysics community. So I want to get this straight, that I picked up, I think, maybe 5 pieces of what to me sound like objective data that characterize this object. One, that its light changes by a factor of 10. So it's got this reflectivity component. Then 2, it came from the local standard of rest, which I think you mentioned is you would expect this from maybe 1 in 500 such objects. Then it's being pushed away from the sun by a force that isn't gravitational. It's not outgassing, anything like that. Then, of course, is the fact that it's interstellar, which is quite anomalous in its own right. And then you also mentioned that there's 90% evidence that this object could be flat and not cigar-shaped. So is this generally agreed upon, these 5 bits of evidence, by the scientists who don't think it's alien in origin? And just to what degree, I mean, I don't know if you can put a number on it, does this make this object an extraordinary outlier compared to the other objects we observe?
Yeah, so this was the first reported interstellar object. So that adds to the mix in the sense that the first thing you see in the street is usually a typical thing. If you see a person, that's the kind of thing you find on the street. And so why would the first one be so different than what we are familiar with in the solar system? And even if you assign a 10% probability to each of these factors, 10% that it would be that extreme in its shape, 10% that it would be pushed away from the sun without showing a cometary tail, 10% that it came, even though it's 1 in 500, it's not 10%, it's 1 in, so 1 in 500 is a much smaller likelihood. When you put all these factors together, you get a very small probability. Okay, for getting the first object, if it's typical, to belong to this class, with these characteristics. And that's what pushed me in the direction of saying, well, it may not be a rock. It's just like finding a tennis ball in your backyard and saying, I'm familiar with the rocks in my backyard, and this may have been thrown by a neighbor. So that was my rationale. I basically did not conclude anything from it. I was just saying, let's find more of the same. Okay, let's look at other interstellar objects. It could be meteors, it could be just passing near the Earth without colliding with it. And let's just check if any of them is technological in origin, simply because they look different. Okay. Now, if you have an agenda of claiming that anything in the sky must be of natural origin, then that brings you to the point of view of not investing in the search. And I say, you can argue, like, quote Carl Sagan, that extraordinary claims require extraordinary evidence. I don't have a problem with that, but my point is different. I say extraordinary evidence requires extraordinary funding. So the point of science is seeking the evidence. If you're not seeking the evidence, if you say, I don't want to look through Galileo's telescope, you will never find this evidence. So it's a self-fulfilling prophecy to say, I don't have extraordinary evidence, therefore I should not search, therefore I don't have extraordinary evidence, therefore I should not search. Then you will never find anything. I would argue that searching for supersymmetry was done despite the fact that you may argue it's extraordinary. The mainstream of fundamental particle physics was engaged with the idea of extra dimensions for 5 decades, 50 years, the lifetime of a scientist, okay? They engaged with the idea of extra dimensions without having any evidence for it. To me, claiming that you have more than 3 spatial dimensions that we can't see, to me, it sounds extraordinary. Nevertheless, nobody said extraordinary claims require extraordinary evidence before they started to get engaged in extra dimensions within the theoretical physics community. And they were engaged with it for 50 years now. In the mainstream, thousands of physicists, the best minds, some of which advertise that string theory is leading the way of physics. People like Brian Greene, okay? Like Michio Kaku would argue, string theory is the frontier of science, frontier of physics. We don't have any evidence for extra dimensions. Why isn't that an extraordinary claim? Why isn't that not followed or not funded because it's extraordinary? The answer is, without building the Large Hadron Collider, we would never be able to test supersymmetry. So you need to invest funds. You need to, in order to get that extraordinary evidence. And in the case of the Large Hadron Collider, we invested the funds. We didn't find for supersymmetry. Okay? So nobody says that was not the right way to do science, because in order to find the extraordinary evidence, you have to divert extraordinary funds to do that, because it doesn't come to your lap. Things that come to your lap without funding, already came to our lap. We saw birds, for many millennia. Then the Wright brothers imitated them. We saw birds. We were able to imitate them. This is an example of something that came to our lap. We see the sun fusing hydrogen. Okay, we are able now, this past year, we were able to produce it in the laboratory. That's the kind of things that fall to our lap. But the frontiers of science got to a point where you need to invest extraordinary funding to find new evidence to promote our knowledge. What we already know is, something of the past. If you want new knowledge, you have to invest to seek the evidence. And so in the context of extraterrestrials, we know that we exist, and we know that planets like the Earth with similar conditions on them are very abundant, okay? And therefore it makes complete sense to search for things like us, okay? You look at the mirror and you say, okay, there might be other people out there like me. So, including Elon Musk, who actually used the Tesla road tester that he had. They put it as a dummy payload and launched it into space. So if he is launching into space his Tesla, why is it so ridiculous to imagine other entrepreneurs on planets around other stars sending junk into space? So there should be a lot of space trash, and some of which, may come our way. So imagine a Tesla passing near the orbit of the Earth around the sun. Obviously, the astronomers would say, well, maybe it's a hydrogen iceberg, a nitrogen iceberg, a dust bunny or something, because we don't see any evaporation of this object. And it would reflect sunlight, and maybe, if it's sufficiently thin, the walls are sufficiently thin, it will be pushed out. Actually, we didn't have that experience, because 3 years after Oumuamua was discovered, in September 2020, the same telescope in Hawaii, Pan-STARRS, discovered another object, which was definitely pushed by reflecting sunlight without a cometary tail. And within 3 weeks, it was given the name 2020 SO. Within 3 weeks, they realized, if we go back in time, actually this object came from Earth. It's a rocket booster. that was launched by NASA in 1966, and it had very thin walls. So it was part of a lunar lander mission. So we discovered our own product. 2020 SO was artificial, obviously. It had thin walls made of stainless steel. That's why it didn't evaporate. And it was pushed by reflecting sunlight because it was thin. So we know that it was artificial because we made it. The question is, who made Oumuamua?
Yeah. And, we haven't talked about the sorts of functions that the two meteors might have had were they extraterrestrial. But sticking to Oumuamua, you averred earlier that, two possibilities. One, that it might be a light sail or a light sail propelled object, or two, that it might be a fragment of this interesting, well, we would call it science fiction, given that we don't have this.
But I would call it space trash, basically. It could be just space trash, a piece of a layer. Of
the Dyson sphere, anyway. But this then raises the question, though, how, given the incredible, almost incomprehensible vastness of space relative to the size of these objects and to us, why of all places you think Oumuamua might have ended up here, only to do apparently nothing?
Right. So there could be two types of objects: space trash that have no functional purpose. They just think about Voyager 1 billion years from now. Okay, it will not be operational. It will be just, and if it collides with another planet, it would appear as a meteor. And then you can, if you find it in the ocean floor of that habitable Earth-like planet, you would recognize that, it had material strength tougher than iron because it was constructed as a spacecraft. That could be, but it's a piece of junk. That's why it collided with the planet. So think of Voyager appearing as a meteor. That's one class of objects in 1 billion years, okay? Not functional. But another type of objects is functional devices. And that, for example, could target the inner region of a planetary system like the solar system, where it might have liquid water that is useful as fuel. You can use the starlight to break the water molecules into hydrogen and oxygen, and then use those as fuel. And one place to refuel in interstellar journey is to visit every now and then the habitable region of a planetary system like the solar system, the region where the Earth moves around the sun, where liquid water is in abundance, because water ice is much more difficult to excavate. So in that case, if you see a certain number of objects in the vicinity of Earth, Earth's orbit around the sun, it will not be representative of the average number of objects per unit volume in the interstellar medium, because they prefer to visit those regions close to stars every now and then. And so there would be many fewer of them. Like I did the calculation, it's about a factor of 10 billion less objects if they are targeting the habitable region around the stars like the sun, compared to a situation where you have objects on random trajectories that fill up space uniformly. The other thing I thought about is that, I wrote a paper about galactic kites. These are films that are less than a micron in thickness. You can show that the radiation force pushing them from all the stars in the Milky Way galaxy is strong enough to lift them relative to the gravitational pull that the disk of stars of the Milky Way has. So if you were to send those kites into interstellar space, they would just hover above the galactic disk. So you can imagine this being, a fun project for an intelligent species, or something to brag about. You just lift those kites and monitor them or use them for some purpose. But if they're easier to manufacture in terms of having many of them, because They are thin. They don't carry as much mass as solid spherical objects, and they would be carried away by radiation over great distances. So the other thing to keep in mind is that all of these physical objects that are launched by chemical propellants, or by radiation pressure, they would move at speeds that are far, at least an order of magnitude below the escape speed from the Milky Way galaxy. So the Milky Way galaxy will keep them bound by gravity. And that's very different from radio signals that move at the speed of light, which escape the Milky Way galaxy. So if a signal was sent 1 billion years ago, it would be 1 billion light years away from us. It would be far away. We wouldn't be able to detect it. Whereas if a package was sent into the Milky Way galaxy with chemical propulsion, it would accumulate over time in the volume of the Milky Way galaxy, just like plastics accumulate in the ocean. In 2050, the amount of plastics in the ocean, in our oceans, the mass of plastics would be similar to the mass in fish, which is something to worry about, because that means that the fish will eat the plastic. They already eat it, and we eat the fish. So we will have more plastic in our bodies, and that's a big risk, health risk in the future.